Welcome back to the third video in the sixth lecture of Covidenomics. Let me just start off by reminding you where we've got to in the first two videos in this sixth lecture. We started off in the first video by noticing an empirical fact, a stylised fact, from a whole range of countries that have been pursuing different policies for the pandemic. And that is that in a whole range of countries, the effective reproduction number for the virus seems to move towards 1 and stay around about 1 over time. Now that changes a bit when governments, for example, lock down the economy. But it is amazing how many different countries have this same pattern in their reproduction number. It starts off perhaps 2.5, 3, 3.5, but fairly rapidly moves down towards 1. We then moved on to the video 2, and we asked what is going to happen to our standard epidemiological model if we include some economics, if we include a simple model of consumer choice about social activity. And we had two parts to that. The first part was based on just a simple idea that we enjoy social activity, but if we do more social activity in the middle of a virus, that creates risks. And we're going to trade off the risk versus the benefit. And if the risks are higher, for example, if there's more infected people in the population, then that will tend to reduce our choice of social activity. If there are few people who are infectious, then social activity is pretty safe and we'll do more of it. The second thing that we did was to allow for the fact that the reproduction number will depend over time on the level of social activity. So in thinking about the effective reproduction number for the virus, if there's lots of people engaging in social activity, they're meeting lots of other people, we would expect that number to go up. If the level of social activity drops, we would expect the reproduction rate or reproduction number to go down. So we'd expect a high level of activity to be associated with an increase in the number of infections because the reproduction number's high, a low level of social activity to be associated with a decrease in the number of infected people over time. We're not mixing with many people, so the virus has less chance to spread. We put those two together to get a very simple economic model, or economic epidemiological model of the virus transmission. And that's based on the work by Joshua Gans, and I gave you the references last time. Importantly, the implication is that in this economic epidemiological model, we will head towards an equilibrium where the effective reproduction rate is about 1. Now, there was a critical assumption in there, which we'll address at the end of this video, about the number of susceptible people in society being constant. We'll come back to that and show how that changes the model. It means it doesn't quite fit the empirical facts as nicely as we would hope. But first, let's take this economic epidemiological model and think about its implications for our predictions about the course of the virus and also for government policy. Let me start by reminding you, though, of how the model works. Here's our A-star level. That's the level of activity such that delta I equals 0, or in other words, we get the same number of infected people each period. So if we're above that line, we have a higher level of social activity. That means that delta I is greater than 0, the number of infections is increasing. If we're below that line, delta I is going to be less than 0, the number of infections is decreasing. Secondly, we've got our social activity curve. So what's our social activity curve doing? Well, it's simply saying for a given level of I on n, so a number of infecteds as a proportion of the population, that's going to set a particular risk associated with social activity, and that's going to influence the amount of social activity that individuals choose. In particular, if we're back here at a low level of I on n, that's going to mean that people choose a pretty high level of social activity. But notice, of course, that we're in the region here where the number of infected people over time is going to increase, so that's going to tend to push our starting point to the right. Conversely, if we start off over here with a pretty high level of infected people as a share of the population, well, that makes it pretty risky to engage in social activity. So individuals are going to choose a lower level of social activity down here. And of course, that's now in the region, it's below this A star line, so it's in the region where the number of infections is falling. So if we start off over here with a high number of infections, people will choose a level of activity that starts to pull the number of infections down. Put this together and it means that we're going to tend to move along this social activity curve to get to our equilibrium here. And our equilibrium is going to be associated with a particular level of social activity and a given share of a population being infected. So that means that the number of new infections each period must just equal the number of people who are recovering, so that our number of infected as a share of the population remains constant. Now remember though, that this does include our assumption, our simplifying assumption, that S, the number of susceptible people in the population, is not changing. And we know that's not quite true, so that's why we're going to come back to it. But I keep on emphasising this. It's a simplification. As Joshua says, it's a shortcut so that we can solve the model simply, and I can present it to you here in these videos. So that gives us our first important conclusion from this model. Given the number of susceptible people, then people's activity, their choice of activity level, will tend to drive the effective reproduction number to 1. Why is this so important? Well, because the predictions that come out of this sort of model, where we're moving to this constant level of infections, are completely different to the predictions that we get out of standard epidemiological models that assume that exponential growth early on, then the virus starting to peak at herd immunity threshold and then dying out. What we get from this sort of model is going to look very different. So if we're making predictions about, for example, number of deaths based on a standard epidemiological model, when what in actual fact is happening is this sort of endogenous choice about social activity which leads to endogenous levels of infection, then our predictions are simply going to be wrong. And we need to modify them to allow for this economic behaviour. Our second conclusion is that while we get to a particular level of infections due to this endogenous economic behaviour, there's no reason why that's going to be the socially optimal level of infections. In fact, there's good reason to think that it probably won't be. Remember, when you're taking into account the amount of social activity you want to do, you take into account your risk of infection and the cost to you of infection. But there are externalities, because if you get infected, you can infect other people, and you don't take those externalities fully into account in general. So we would expect that when we get to this level of infections, when we get to this effective reproduction number of 1, that there's still a role for government policy here. We're not getting to the optimal level of infections from a public health, a public welfare perspective. The third thing to note from our model is that we will expect different countries to get to different outcomes whenever the costs and benefits of social activity differ between countries. So we've got a couple of examples here. Let's assume that A stands for Australia, whilst B, let's make that Bangladesh. Well, in Australia, when you have social activity, you get fun, but social activity includes more than simply going to parties or going to the gym or going to the cinema. It includes things like working. And if you don't work in Australia, well, what the government has done is they've said, we will compensate you. They've brought in ideas like JobKeeper so that people can be compensated for not engaging in social activity, including work. Well, that reduces the benefits of social activity, and we would expect the social activity curve to look like this one here. Contrast, let's think about poorer countries like Bangladesh. If you don't go out to work in Bangladesh, then in general you're not going to be paid. So that means that there is a lot bigger cost to an individual and to their family from reducing their social activity. So for any level of risk of infection, we would expect that, say in Bangladesh or India, Pakistan, parts of Africa, we would expect people to choose, given that risk, a higher level of social activity. In particular, going to work and getting paid, because the alternative of relying on government compensation is either much lower or non-existent. So we would expect the social activity curve in Bangladesh to be above the curve that you get in Australia. What does that mean? Well, they're both going to move towards this equilibrium where you have a constant level of I, or a constant fraction of the population infected, an effective reproduction number of 1, but they're going to be at different levels. It will involve more people being infected every day in Bangladesh than in, say, Australia. And again, that tends to be in line with the empirical evidence that we've seen during COVID-19 pandemic. Fourthly, let's look at government policies to deal with a pandemic. Let's look at policies that don't directly affect the level of social activity, but rather that address the chances of becoming infected. So, for example, social distancing rules, or a simple one that fits nicely is the policy where you have to wear a mask in any public place outside your house, one that we currently have, for example, in Melbourne here in Australia. We're just going to do a couple of things. Let's deal with these in turn. The first thing it's going to do is it's going to raise that critical level of social activity that's associated with a constant level of infections, or an effective reproduction number of 1. How can we see that? Just remember, this is the equation that we're interested in that gives us that delta I on n equals 0. And if we have mask wearing, well, that's going to mean for any level of social activity A, the probability of being infected or infecting somebody else is going to drop. Mask wearing is a deliberate attempt to reduce this reproduction number. Now, given ST, given N, and given gamma, our rate of recovery, then as mask wearing pushes down beta, well, the level of social activity, so that delta I is 0, is going to be able to go up. That's going to push beta back in the other direction. So we'd expect our critical A value, our critical activity level associated with delta I equals 0, to be higher under a mask wearing policy. The second thing that a mask wearing policy is going to do is that it's going to reduce the risks associated with social activity. Because everyone's now wearing a mask, you can engage in social activity, and even though there might be just as many infected people out there as before, you're less likely to catch the virus from them. So that means that for any given level of I on n, you're going to tend to optimally choose a higher level of social activity than you would have before. Or in other words, a policy like mask wearing is going to shift our social activity curve up. Let's put these two things together. So, if you introduce mask wearing, then the level of social activity that is associated with delta I equal to 0 goes up, and the individual social activity curve or social activity choice curve will also tend to go up. What does that mean for the course of our virus? Well, we're going to move from our initial equilibrium here to our new equilibrium up here. As I've drawn it here, that's going to mean that we do in fact have a reduction in the number of infections per day, or the number of new infections per day in equilibrium in society. So the mask wearing policy, as I've drawn it here, is working in the sense that it's repressing the number of infections or reducing the number of infections. But the effect is partially offset by this increase in social activity. So if you simply introduce mask wearing, you would expect people to respond by engaging in more social activity than otherwise, quite sensibly from their perspective. Further, note that I could have drawn this differently. While A goes up, the social activity curve goes up, I could have had this increase bigger compared to this increase. And if I'd done that, I still would have got the rise here in the level of social activity, but I could have got the perverse result where mask wearing actually increased I on N. Now, to see whether or not that's actually possible, you need to go into much more detail in the modelling than we're going to do here. So the critical takeaway here is that a policy like mask wearing, which doesn't directly impact social activity, but does impact the risk associated with social activity, will tend to work against itself. By itself, without any backup, you'll tend to get this increase in social activity when you introduce such a policy, and that can partially offset its effectiveness at combating the number of infections and the spread of a virus. Next, consider a government policy that does directly restrict the level of activity. Now, we've got one on here, we've got a maximum level of activity that can be engaged in. So this is a lockdown. Businesses are required to shut, people have to stay home, you're only allowed to leave home for certain activities. You can't go to a pub or go to the cinema or in many cases even go to work. What's that going to do? Well, notice that now our activity level is going to be less than the activity level associated with a constant I. Or in other words, we're going to be down in this zone where the change in I is less than 0, where I is falling. So such a policy that restricts activity will have the effect of pulling I on N back here to the left. It will reduce the spread of the virus, it will reduce the number of new infections each day. But suppose when the level of infections gets down here, the government decides to remove the policy. Now people can re-engage and choose the preferred level of social activity. Well, what activity level will they choose? Well, given that number of infected people in society, they're going to choose an activity level up here. But this level of activity is in the zone where delta I is greater than 0, or in other words, the level of infections is going to start rising again. So as soon as the government lifts the policy, we're going to start moving back towards this equilibrium level of infections. So we get this sort of bounce back as soon as the restrictions on social activity are removed. Yes, they can reduce the level of infections while they're in place, but when you remove them, people are going to increase their level of activity, and that's going to start the rate of infections going up again. And of course, we've seen that in a variety of countries that have lifted their restrictions on activity and then been surprised when people go out into the streets, they start socialising again, and the number of infections goes up. It's just simply rational behaviour from the individual perspective. Our sixth lesson relates to things that will occur in the future. So for example, let's suppose that a vaccine is near. Well, that doesn't necessarily change your risk of being infected today, but it does change the costs of being infected compared to not being infected tomorrow. Or in other words, now, if you can avoid infection for a little while, you'll be able to get the vaccine and you won't have to put up with the problems associated with being ill with the virus, potentially dying. So that's going to tend to increase the relative benefits of staying well compared to being sick. So if we think a vaccine is near, we would expect to see the optimal level of social activity for any given level of I on N. We'd expect to see that optimal level of social activity fall, or in other words, our social activity choice curve to move down. We're going to move from our initial equilibrium to our new equilibrium, same level of activity and equilibrium, but a lower level of I on N. In other words, as individuals reduce their level of social activity, the virus numbers reduce. As the virus numbers reduce, then they'll tend to start increasing their level of social activity again, but it's always going to be in a situation where we've got a lower overall I on N value compared to the one when the vaccine was theoretical and far away. One lesson here is that governments have to be very careful about policies that do the reverse, that reduce the cost of becoming infected. For example, early on in the pandemic, some people suggested, well, those who have been infected have antibodies in their system, they can't get infected again, so maybe they should be allowed to go back to normal living, go to work, go to school, go down to the pub, have parties, whatever, even though everybody else should remain locked down. Now, it was recognised pretty early on that was a bad idea. Why? Well, because if you reduce the costs of being infected, in fact, if you make it desirable to be infected, well, people may choose to get infected. And with some other diseases, we've actually seen people have parties where they invite along somebody who they know has the disease, and everybody tries to catch the disease off them so that they then get immunity and get the benefits of that immunity. We sort of don't want that with COVID-19, where a certain number of those people will die. While having a party to get infected is an extreme case, it does suggest the government needs to be careful that when they're thinking about policies to reduce the future cost of being infected with COVID-19, that may lead to endogenous changes in activity choices, which can actually speed up the spread of the virus. Now, a few times we've referred to this assumption in our model that ST, a number of susceptible people, doesn't change. And of course it does. As more people become infected, that reduces the population of susceptible people. And that's the basic SIR model logic. The number of susceptible people drop over time as the virus spreads, and those people become either infected or have recovered or have died from the virus. So we know that ST, a number of susceptible people, is going to decrease, possibly slowly over time. It's going to depend on the number of infected in our population. This means that within this model, we're going to get a change in the critical value of activity associated with delta I equals 0. We can see that from our simple equation here from the SIR model. Given the level of gamma, that recovery rate or recovery proportion, if ST is falling over time, then to keep delta I equals 0, beta must be rising. Or in other words, remembering that beta increases in our social activity level, that means that the critical level of social activity, so that this equation holds, must be going up. And if that critical activity level goes up, that means that we would expect the number of infected people, I, to fall slowly over time. So in other words, our model actually doesn't quite predict an effective reproduction number of 1. It predicts an effective reproduction number of a bit less than 1. So here's our last lesson from our simple model here. And that is that as the virus progresses, the number of susceptible people falls, the equilibrium number of infections will fall, and the equilibrium level of social activity will rise. That's what we've got here. As the number of susceptible people fall, our critical level of activity rises, so we've got it going up here. And as that occurs, that's going to mean that our equilibrium goes from here to here, and our value of I on N associated with that equilibrium falls. So within this model, actually I won't be constant. It will slowly decrease over time. The effective reproduction number will be slightly less than 1, and the virus will slowly die out. As I said at the beginning of this video, we're dealing with an active area of research in this set of videos, and possibly by the time you're watching it, there will be more advanced models out there that join the economics and the epidemiology and come up with better predictions than the one we've got here. But the broad lessons that come out of this model are likely to still stay the same. The fact that you can have government policies working against themselves, the differences between government policies, that potential for bounce back. If you restrict social activity, then reduce the restrictions. And the fact that the predictions you make, if you don't take economic policy or economic behaviour into account, are going to generally be pretty inaccurate, and we want to improve them by adding economics to these epidemiological models. So let's just summarise where we've got to in these 3 videos. We've looked at the empirical evidence that suggests the effective reproduction number for COVID-19 tends to be around 1 in a whole range of countries that have very different policies, that have very different economies. We've introduced human behaviour to try and explain this. We've introduced an endogenous choice of social activity. The predictions for the course of the virus that come out of this epidemiological model, where we've included human behaviour, are very different to the sort of predictions you get from a standard SIR model. So including human behaviour can shed a lot of light, both on the course of the virus and on different government policy options. And finally, this is an area of ongoing research, and the material here is a long way from the final word on the topic. Thanks for listening. I'm going to include another video, a 4th one of this series, just running through a little bit of a maths behind that social activity choice curve. Feel free to skip that if you don't want to see it. Talk to you next time.